Line it up with the mark. Got it? Perfect. Set the stake.
There are construction projects that change a city. And then there are projects that have to stay completely invisible. Somewhere beneath millions of people, machines larger than apartment buildings are carving through the earth every single day. Not beneath empty countryside, not beneath newly developed land, but beneath streets that have existed for centuries. Now imagine what happens if one calculation is wrong. Not by a meter, not even by a foot, just a few centimeters. That tiny mistake could crack foundations, damage priceless landmarks, or bring one of Europe's busiest cities to a standstill. So why would anyone take that risk? And more importantly, how do engineers build the largest underground megaproject in Europe beneath a living city that never stops moving? The answer isn't just bigger machines. It's a completely different way of thinking about construction. And by the end of this video, you'll see why the hardest part wasn't digging the tunnels at all. Most megaprojects begin by clearing the land. This one had no land to clear. Everything that already existed had to remain exactly where it was. Homes, businesses, railways, utilities, historic buildings, millions of daily journeys. The city above had to keep functioning while another city was quietly being built underneath it. That single requirement changed every engineering decision that followed. Because before a single tunnel could be excavated, engineers first had to solve a problem hidden beneath the streets.
Keep the blankets overlapping. Okay, spraying this section now. Looks good. Let's check the moisture here. Keep it steady. Down a little. Watch the corner. It's too far right. Slowing down. Give it a gentle nudge. That's better. Check the plumb. Hold it there. Ease it down slowly. Copy. Adjusting position. Watch the taglines. Final check.
Maps only tell part of the story. Below the streets lies a maze of forgotten infrastructure. Old tunnels, abandoned foundations, water pipes, sewer systems, power cables, communication lines. Many dating back generations, some with incomplete records. Before construction could truly begin, engineers spent years discovering what was already underground. Every unexpected obstacle forced the route to change. Every route change affected future stations, and every station changed the geometry of the tunnels. Then came the geology. Unlike solid mountain rock, the ground beneath the city constantly changes. Clay becomes limestone. Limestone becomes sand. Sand suddenly becomes water-bearing gravel, sometimes within only a few hundred meters. Each layer behaves differently under pressure. So how do you build a tunnel through ground that refuses to behave the same way twice? The answer came in the form of giant tunnel boring machines. But these aren't simply enormous drills. They're moving underground factories. As they advance, they excavate soil, stabilize the surrounding ground, remove thousands of tons of material, and install permanent concrete tunnel rings almost simultaneously. Every meter forward depends on thousands of calculations happening in real time. Engineers continuously monitor pressure, alignment, vibration, and ground movement. Because success wasn't measured by how fast the machines advanced. It was measured by whether the city above noticed anything at all. Surprisingly, the tunnels were only half the challenge. The stations were even harder. Unlike a circular tunnel, a station requires enormous underground caverns. Entire sections of earth must be removed while supporting everything overhead. Temporary retaining walls, ground anchors, massive concrete slabs. Every excavation had to follow an exact sequence. Dig too quickly, and the surrounding ground could shift. Move too slowly, and the entire construction schedule begins to unravel. And then another invisible enemy appeared: water. Groundwater doesn't need dramatic flooding to stop a project. A slow leak can weaken soil. Pressure can deform structures. Unexpected inflows can halt excavation for weeks. That's why engineers designed waterproofing systems before the first train ever existed. Every concrete segment, every seal, every joint, every station wall, built to resist decades of underground pressure. But even after solving geology and water, one final challenge remained: keeping one of Europe's largest construction projects moving without the city ever slowing down.
The stress points look good here. Note the wear on cutter head 3, sector 7. Tablet data confirms tolerances are acceptable.
Lift clear of the shaft.
Hold it steady on the taglines.
Swinging to the transport area now.
Line it up, right there. Send it down. Engage the tool. Secure the connection. We're good.
Keep it steady. Guide it in. Aligning. Ready for impact. Line 3, mark the conduit. Secure the trays to the beam. Check the fitting on the high voltage. Verify the duct alignment here.
Section is complete.
Check cable tension on that bundle. The level needs to be precise.
Adjust the rod to match.
Verified, ready for pour.
Keep it slow and steady, that's perfect. Just a little to the left.
To the left.
Grab that crimping tool. All right, bring it closer. Careful. Hold it there. Just a fraction to the left. Got it. Secure it. Keep it steady. Guide it in. Slow down.
Lower.
Lower. Lock it in. Tighten the bolts.
Status check. Systems are stabilizing. Confirmed. Moving to damper adjustments now. The front of the train has just cleared the first sensor.
Confirmed. Platform integrity is stable.
Proceeding with the stopping sequence. Sequence 1 complete. Initiating sequence 2. Timing check positive. Doors cycling. System check initiated. Communications optimal. Monitoring train control performance. The intake readings are stable. Flow rates are optimal.
Unlike most
Monitor the
mega
east
projects,
extraction
this
points.
wasn't a single construction
Evacuation
site.
teams report to
It
Sector
was
B.
dozens operating
Sector
at
B
the same
confirmed.
time.
Proceeding with
Multiple
verification.
tunnel boring
Check
machines,
emergency lights
thousands
and
of
signage.
workers,
The sealant is
hundreds of
perfect, just as
contractors.
specified.
Check the
Every
calibration
schedule
on the scanning
depended on
tool.
another.
Verified. The
One
finish is
delay
flawless.
could ripple through the
Let's
entire
proceed to
project.
section 2.
When
Time
it's fully
check.
complete,
1 minute
this
to
won't just be
departure.
another metro
Automated
line.
sequence
It will
initializing.
transform how
Traction
millions
engaging.
of people move
Speed
across the
nominal.
Paris region,
Departing.
cutting travel times and
Systems
connecting
check green.
communities that were never directly linked before.
Ready for handover.
But the greatest engineering achievement isn't the size of the
Excellent.
project. It's that almost nobody will ever notice what it took to build. Passengers will simply step onto a train and travel beneath one of Europe's busiest cities, never realizing they're passing through one of the most ambitious underground construction projects ever attempted. That's what makes great engineering truly remarkable. When the impossible becomes so reliable, it feels completely ordinary. If you enjoyed this deep dive into the world's greatest engineering mega projects, don't forget to subscribe for more.
Cable trays look secure, no fraying. Rail fasteners are tight, no anomalies on the sensor. Data matches specifications, integrity confirmed.